Minash-shaytanir-rajim. Bismillahir-rahmanir-rahim. Assalamu alaikum warahmatullah. Welcome to the third lecture of week 5. So in the last few lectures we have been discussing chapter number 19 of our course book, that is the bulk deformation process. So in the previous lecture we have discussed the rolling operation as well as the forging operation, and I told you to read some special rolling processes towards the end of the rolling topic in your course book, and we will discuss some specialized type of forging process in our live sessions. So now let's start with the extrusion process. So as we have discussed time and again that the bulk deformation processes in general are compressive in nature, so do the extrusion process. So extrusion process is a compression metal forming process in which the work metal is forced to flow through a die opening to produce a desired cross-sectional shape. So what we have a cavity with dies towards one end, and metal is fed into that cavity, while there is a ram at the opposite end of the die that is pushing that metal and forcing it to squeeze out of the die opening. So this is how we ultimately have a long, you can say a long rod of this material with the cross section same as the die cavity. So this cross section depends upon the die opening. So this process is, if you must have observed in your daily life, is similar to the squeezing the paste out of the tube. So in the morning when we perform the toothbrush, so when we squeeze that paste out of the tube, so the extrusion is similar to that one. So in general, extrusion is used to produce long parts or uniform cross section. So this is the advantages as well as the limitation of this process. If you want to have a long uniform cross section of any material, you will prefer the extrusion process, and the extrusion process is capable of producing this cross section only. So this is the advantage and the limitation of this process as well. If you see some advantages of this process, so if you check out the advantages of the extrusion process, it is capable of producing variety of shapes, especially in the hot extrusion, as we have discussed time and again that hot working process are capable to produce significant plastic deformation and a shape change. Second one is limitation, as we have discussed in the last slide, that the cross section that can be produced using the extrusion process is uniform throughout the length. So this is one of the advantages as well as the limitation of this process. Especially in the cold extrusion, the grain structure and the strength can be enhanced because of the compressive force that are induced onto the material. So the grain structure can be oriented in certain directions, and so the strength can be enhanced using this process. Because of the very well defined die openings in towards the end of the container, so we have close tolerances possible, like the dimensions which we'll achieve at the end in our product will be very much accurate. So in as we have discussed in the bulk deformation process as a whole, the waste of the material is almost negligible in most of the bulk deformation process. So if we check out the classification, so the extrusion process can be classified based on three parameters. The first one is the direct and the indirect extrusion. Second one, as for all the case for all of the bulk deformation process, is the based on temperature, that is a hot extrusion and a cold extrusion. The third one is a discrete extrusion and the continuous extrusion. So what is a direct and indirect extrusion? A direct extrusion is also known as a forward extrusion, because in this case we have a die at one end of the container while the ram is at the opposite end of the container, and in between there is a work material in the form of work billet. The work material, the material which we feed into the container, that is called as a billet. So the billet is in between, so the ram forces the material to squeeze out of the die opening. So the force is applied on one direction and material is squeezed out of the opposite direction. So that is why it is called as a forward extrusion or the direct extrusion. So the extra, as we know, when the ram keep on pushing this material and squeezing it out of the die opening, when the ram reaches at this extreme edge, when the ram approach at this extreme edge, so there will be still some amount of material left here. So this extra material that is left here, which cannot be squeezed out using this frame, that is known as the butt. So it must be separated using some cutting operation or some trimming operation. Starting billet cross section is usually round. Obviously this is the section view of the extrusion container, so it is usually the round cross section, the work material, but the final shape is determined by the die opening. So the final cross section would be determined by the die opening. It can be of any shape based on the die opening, the die angle, so on and so forth. So from the direct extrusion we can have a solid part as well as the hollow one. So if we want to have a hollow one, we have a ram and a mandrel is attached to it. So we attach a mandrel, and while feeding the billet, the starting material into the container, we pierce some hole so that the mandrel gets into that billet. So once we exert force, so that the material which will squeeze out of the die opening will be hollow. One of the restriction in the let's jump towards the indirect one. Leave it for now. The other classification is that the indirect extrusion. So the indirect extrusion, it is also known as a backward extrusion or the reverse extrusion. As we have seen the direct one, what was the direct extrusion, in which the force is applied on one direction and the material is squeezed out from the opposite end. And while in the case of the indirect extrusion or the backward or the reverse extrusion, the force is applied in the direction while the material is also squeezed in the same direction, from the same side. So we have a ram or the die attached to the container. The ram and containers are assembled together and the billet is fed into the container. So the ram squeezes or ram compresses the material so that it is squeezed out of the die opening from the same side. So that is what is called as the backward extrusion and the reverse extrusion. So in the case of the backward extrusion, we can have both the hollow part as well as the solid part. So if you want to have a hollow part, we will have a ram toward the center while the clearance is between the ram and the container. While if you want to have a solid part or the solid rod of the material, the clearance is given within the ram. So there are a certain restriction of the indirect extrusion is that we cannot extrude out the long sections. One of the difficulty or one of the disadvantages is that long sections cannot be extruded, or long, you can say long parts cannot be extruded. Why is that so? Because if we keep on compressing this work material and it is squeezing out in this direction, so at some point of time we will have to support the ram, obviously. So at some point of time when there will be its length has increased a lot, so we will have a difficulty in supporting the ram from this direction. Obviously the ram will be attached to some mechanism here. So once the part length has reached here, so we will have a difficulty in further squeezing or further compressing the work material within the container. So that is why long sections cannot be extruded in the case of the indirect extrusion, while it can be easily extruded in the case of the direct extrusion. But one of the advantage of the indirect extrusion over the direct one is that if we see the direct extrusion, when we forces the work material in this direction, so this material slides over the container surface. So there's a resistance or the friction between the container surface and the work material. So because of this friction effects, we need to have some extra force to perform this extrusion process. There's a relative motion between the work part and the container. While in the case of the indirect extrusion, if you see here, there is no relative motion between the work part and the container. The work part is simply passing through this clearance. Only the ram is piercing the work part and forming a cavity, while in this case the work part is passing through here. There is no relative motion between the container and the work part, so there is no friction effect. So the force required in the indirect extrusion, is lower compared to the direct one, right? Because of, you can say, negligible, for now, negligible friction effect, right? So this is a certain differences between the direct and the indirect extrusion. So the first classification of the extrusion was based on the movement of the work material. When we apply the force in one direction and the material is squeezing out in the same direction, we say that it is a direct extrusion. Or we can say when we are applying the force from one end, material is squeezing out of the opposite end, that is a direct extrusion. And we can have a hollow and the solid parts, and we can have a longer length sections in the case of direct extrusion. While in the case of the indirect one, the long sections are not possible, and the identification is that we are applying the force in one direction and the material is squeezing out from the in the opposite direction, right? So this is the indirect extrusion. Long part cannot be extruded in the indirect one, while the frictional effects is negligible in this case because there is no relative motion between the work part and the container. So that is why we need to we can have a lower force in the case of indirect extrusion compared to the direct one. So let's jump to the second classification of the extrusion process, and that is, as we have discussed time and again, that is based on the temperature. So we have the hot extrusion and the cold extrusion. Hot extrusion means we are performing this process at the hot working temperature. And what was a hot working temperature? That was approximately 50 to 70% of its melting point, right? 50 to 70% of the melting point of the material we are performing the process on. So prior to the extrusion process, we heat the billet, the material we heat the billet above its recrystallization temperature. So this is the above the recrystallization temperature range. So what is the purpose of performing the hot extrusion? We can reduce the strength, increase the ductility of the material, we can cause a significant plastic deformation and the shape change, and we can reduce the size. Obviously when we have softened the material, we can cause a significant shape change. While in the case of the cold extrusion, it is performed generally at the room temperature or slightly above the room temperature in case of the very brittle material. So our primary purpose is to increase the strength of the work part and to have a part with a very well defined dimensions. So in the case of the cold extrusion, it is generally used to produce the discrete parts. Discrete part means uh, which are not long sections, small parts, right? They're not the long section, individually small parts. There is no formation of long rods and the beams. Rather, we have a small parts, discrete parts. Okay? And we will discuss this later on in our slides. The third basis of the classification is the discrete and the continuous extrusion process. So what is the difference between the discrete and the continuous extrusion process? Continuous extrusion process is also termed as a true continuous extrusion process. Uh, so in the case of the continuous extrusion process, it will be true when we have a steady state mode for an indefinite period of time. Means we are constantly squeezing the material out of the die opening. So this process is used to make a long section, very long section in one cycle, but its length is limited by the amount of material that can be fed into the RAM. So generally it is termed as semi-continuous extrusion process. What does it mean? We have a container here, and this container has a die towards the end, and we have some billet of any material that has been fed into the container, and we are applying the pressure here. So we can keep on squeezing the material up to any length theoretically, but on the practical nature, practically we encounter a problem that the amount of material that can be fed into the container, only this will limit the length of the part that can be extruded in the case of the continuous extrusion. So means we are with the uniform velocity, we are squeezing the material out of this die opening. So A continuous extrusion can only performed as a direct extrusion. A continuous extrusion will always be a direct extrusion, because we have studied in the last slide that indirect extrusion cannot manufacture or produce the longer parts. Only discrete parts can be made in the indirect one. So a continuous process will always be a direct extrusion process. And in the case of the discrete extrusion, single part is produced in the each second. So in the case like as we know, we have a container containing the billet, and it has some billet here. So if a ram pushes into here, so ultimately what kind of what kind of part we will get, it will pierce into this billet. We will have a structure like this, right? And there's a ram inside, and that ram can be removed, so we'll have a cup like this. So in the case of the discrete extrusion, we make a small parts, individual parts, and the force exerted is not of uniform nature, that we are not gradually applying the pressure, rather it is in the impact in nature. And in the when we were discussing the forging operation, we have discussed what the impact load is when we apply the force for a very short period of time, not over the time period, rather a force that is applied for a very short period of time. So that is called a impact extrusion. So a discrete extrusion is performed as a indirect extrusion, right? While the continuous one is performed as a direct extrusion. And mostly this in discrete extrusion we apply the impact loading, so it is also known as an impact extrusion. Now if we move towards the analysis of the forging extrusion process, one of the things that we have left while discussing the direct extrusion, if you see here, when we are performing this forward extrusion as a hot extrusion process, one of the problem we encounter is that, as we know that in the case of the direct extrusion, there is a friction between the container and the work part. But in the case of the hot extrusion performed as a direct extrusion, this problem amplifies. And why is that? So because there's a formation of oxide layer, onto the surface of the work material. Whereas the work material are feeding here, its surface generates some oxide layer. So, and that oxide layer, obviously when you squeeze it out of the die opening, there will be oxide layer on this surface of the work part as well. And it will not only increase the frictional effect but also reduce the quality of the product. So to avoid this, what we do, we add a block that is known as a dummy block. We add a block here that is slightly less in diameter than the billet. We add a block at the ram, ahead of the ram, that is slightly less in diameter compared to the billet. So there is some space left here. So what happens when such ram with a dummy block, this is called as the dummy block. Right? So when such ram with a dummy block forces this material, so the thin layer of the material is left inside the container, while the material deep inside is squeezed out of the die opening. So ultimately, which we achieve at the end is a material without the oxide layer, oxide free. So the thin layer that is left within the container is obviously rich in oxides. So this is the purpose of the dummy block. So it is used in the case of the direct extrusion, and when you are performing a direct one as a hot extrusion. So now let's move towards the analysis of the extrusion process. So as we have the different values while analyzing the various deformation process, like in the case of the Rolling operation, we have find out the draft that is to be produced, that is a difference in the initial and the final thickness. In the case of the forging operation, we have find out the ratio between the initial and the final height. And so in the case of the extrusion, we have a ratio that is known as the extrusion ratio or the reduction ratio, or that is also known as the reduction ratio. So the reduction ratio, that is Rx equals to A naught by AF, where A naught is the initial cross-sectional area, while the AF is the final cross-sectional area, right? So we can find out the true strain using this extrusion ratio. So because our primary concern is to reduce the cross-section area, we have a certain cross-section area A naught, and after the extrusion we have certain cross-section area AF. So the only strain that is being produced here is the cross-section area that is measurable. So the strain, true strain, would be equals to ln of A naught by AF, or we can also write it as ln of Rx, that is a reduction ratio. So now we are under the assumption that this is the ideal deformation and there's no friction that is present between the container and the work part. So under this assumption we will have pressure. In this case we will assume the pressure for calculating that, because why is that so? Because as you know, pressure is always applied normal to the surface. So instead of the stress, we will take it as the pressure. As so under the assumption that this is an ideal deformation and there is no friction in the extra work, so the force that is required has been reduced to the pressure that is being exerted normally onto the surface of the billet. So that pressure is equal to the flow stress that is required for deformation into the strain that is to be produced. But in reality, as we know, that this is not the case. We have a friction that is present between the billet and the work container, and especially in the hot working, that this effect is amplified. So the flow stress in this equation would be the average flow stress. As we know, in the case of the extrusion, especially in the direct extrusion and the hot extrusion, the pressure is gradually applied. So there is a uniform pressure over the period of time instead of the impact load. So the YF would be equals to flow curve into the true strain divided by 1 plus strain hardening exponent. Right. So to take into account the frictional effects, as we know, we have a billet here with the pressure is being exerted with the initial diameter d naught and the final diameter is df, and the contact length between the billet and the container is L. So there is a friction that is acting at this meeting surface. So to take this into account, we have another strain that is known as the extrusion strain. And this is the empirical method that extrusion strain that is known as the epsilon x equals to A plus B ln of Rx, right? A plus B ln of epsilon. You can call it as a epsilon. A plus B ln of Rx, so you can simply write A plus B to true strain. So this is the true strain value and this is the extrusion strain. This is the empirical observation, right? Empirical means it has been observed by experimentation during the practical methods. So here A and B, A is 0.8 and B ranges from 1.2 to 1.5. Okay, and these value depends upon the die angle. Right? These value depends upon the die angle. So for the indirect extrusion, as you know, there is no pressure involved, there's no friction involved that much, so you can have pressure that is being exerted equals to the flow stress into the extrusion strain. But keep in mind the flow stress was equals to YF K into true strain exponent divided by 1 plus N. Right? So this is the true strain. You will use the true strain to calculate the flow stress, while you will use the extrusion strain here in this formula. So this is for the indirect extrusion. But as we know, in the direct extrusion, there is a lot of friction force that is present here at the container and the billet's interface. So, we will take into account the extra amount of pressure that is being exerted in this equation. So for the extra amount of that pressure, that is equals to the pressure we are exerting, the extra pressure for overcoming this friction effect, and that extra pressure is being, as we have discussed, this is the circular cross section. This is the circular cross section here of this whole billet. So this extra pressure is being exerted along this circular body, right? It's cylindrical body, right? So that would be equals to into the area pi d naught square by 4. So this cross section area is equals to pi d naught square by 4. So that extra pressure is being exerted on this cross section. So that should be because we are exerting this extra pressure to overcome the friction. So which friction? The friction that is acting along this whole surface of the billet and the container interface. Obviously the container is also the cylindrical body, this billet is also cylindrical body, so they are in contact along this whole circumference. They are in contact with each other. So the friction is present along this whole contact surface, along this whole circumference for this length, right? So this extra pressure we are exerting on this cross section should be equal to the friction that is present here to reduce its effects. So the friction, as we know, the friction force is equals to mu, the friction coefficient, into the normal reaction. So we have the pressure we are exerting to overcome that friction effect equals to the friction coefficient. And what is the normal force? What is the normal reaction here? That is the pressure at this, the direct pressure that is at the billet container surface interface and along this whole circumference for this whole length. So what is the formula for circumference? As you know that the circumference is equals to pi d naught. This is our whole circumference, and along this whole length, so we have pressure that is exerting along this whole circumference for the whole length of L. So this is the friction that is present at the die, at the container and the billet interface, and to overcome this friction we are exerting this pressure, right? That is the PF into this much. So on the, you can say on this side, this is the let me move it in this way. So on the left hand side we have the additional ram force, this is additional ram force to overcome the friction. while on the right hand side we have the friction force. We have the friction force at billet container interface, right? This is what we have. We have the additional pressure here and additional ram force, that is to overcome friction force, and the actual friction force that is present at the billet and the container interface. So if you take this into account, is this one, if you take this into account, and for the worst case scenario, let's suppose if we have the worst case scenario that there's so much friction because of the hot working that the material has started to stick to the surface of the container, that this billet material is starting to sticking at the surface of the container. There's so much friction here. So in that worst case scenario, we will assume this one we will assume that the shearing is present at this interface. So you can rewrite this equation as this right hand side, because we can rewrite this friction force as friction coefficient, that is a shearing pressure that is greater enough to cause the shear of the material, and the remaining the pi d naught L, right? So this can be reduced to, because this the frictional effects and the pressure, that is so much, that is equals to the shear strength of the material, that the shear strength, yield strength of the material into pi d naught L along this whole force, right? And we have a theory that because we don't have any other method to calculate the shear strength of the material here, so using a theory we call that the shear strength is equals to half of the yield strength of the material, right? That the shear strength is half of the yield strength of the material, or we can call, and in the case of the hot working we know that the yield strength is equal to the flow stress. Flow stress is basically the yield strength of the material. So we can simply rewrite the equation as by placing ys equals to yf by 2. So we can rewrite this equation. We are only working on the right hand side here, then we will equate it back. Okay, so you can rewrite this one as equals to we can solve it for this one. We will have the expression. I'm just directly writing the final answer. This is the extra friction pressure we are exerting to overcome the friction effects, right? So based on this, the formula can be used to compute the ram pressure in the direct extrusion. So we will just simply add, we know the pressure was equals to this one, right? So we can rewrite the equation. So this is the complete expression for calculating the pressure in the extrusion, direct extrusion process in the case of the friction effects, where this 2L by D naught, this 2L by D naught is due to the extra friction that is present at the interface of the container and the work part. So once you have the pressure, you can find out the force, that is equals to F equals to P into A naught, right? Where P is this one, the pressure. This is the extrusion force. So this is all for the analysis of the extrusion process. Now the next topic is the extrusion dies in the orifice. So orifice is a tiny opening, you can say, opening for the flow of material. So in the case of the extrusion dies, as we have seen, let us revise the diagram. This is the container here. We have the dies. This one is the die cavity. This is die, and we have the ram on this direction. This is the billet, the blue one. So the die force, the extrusion force also depends upon this die angle. So if you have a low die angle, the surface is large. If you can see, revise the diagram. If it says if you have a low die angle, the surface area is large, leading to increased friction at the blade die interface. Right? If our die angle is low, we will have to exert extra force to overcome the friction effects. While in the case of the large die, we will have lower friction but more turbulence in the metal while extruding. Why is that so? If you see here, this is the die angle there. So if this die angle is smaller, it means our die surface would be like this. Instead of ending here, it will end like this, right? So this would be the die angle. So if we have the lower die angle, so the contact area of the work material and this die will increase, and ultimately there will be more friction while extruding. So although they will be smooth, the process will be smooth, but it will require more amount of force while extruding a material. But if we choose a large die angle, if the die angle is further increased, let's suppose if we choose a large die angle, let's suppose this one. So this will be the die angle. So although the contact area between the billet and the work part is less, but the work part has to be, there will be so much turbulence while passing the material from this sharp edge. So there will be a very sharp edge here if the die surface is like this one. So we'll have a lot of turbulence while performing the extrusion process. So we have to select an optimum range of the die angle based on the work material, the temperature, the lubrication, and the lubricants we are using. And so is the case with the extrusion orifice. So is the case with the extrusion orifice. What is the orifice? If we look at our basic schematic of the extrusion, we have our dies here like this one. So this opening is termed as the orifice. This profile of opening is termed as the orifice. So the shape of the orifice determines the final shape of the part. So up till now what we have been discussing, we have been assuming that it has a circular cross section. So we have a circular part, right? But we can have different shapes of the orifice as well based on our desired application and the desire or the result we want to achieve in our final product. So if we have a different profile than the circular cross section, we have to add a shape factor in our final formula. That shape factor is equals to kx, as we have discussed in the case of forging and other as well. It's equal to 0.98 plus 0.02 into cx divided by whole exponent 2.25. That is called a shape factor. So if you have some other profile of the orifice other than the circular one, we have to add a shape factor in our formula. So our formula would be pressure equals to kx into the average flow stress into remaining same extrusion strain plus 2L by d0, right? So this will be our pressure base. If we have some other cross section of the work part other than the circular one, so cc here is the parameter if our profile was circular one, and cx is the parameter for the profile we are dealing with. So let's suppose if we have a product that has some rectangular profile, so we'll calculate the parameter of this one all these directions, so that will be equals to Cx. And for the same volume and the length, you will calculate the, if the parameter was circular, so if our profile was circular, what would the parameter, that is Cc. So this is how we can calculate the shape factor in the case of the profile other than the circular one. Now the last one, the machines that are used in performing the extrusion process. We have two kind of the process, as we have seen, in which we apply the gradual pressure to have a long cross sections and that is mostly performed in the direct extrusion, while other one in which we apply the impact loads to have the discrete extrusion process or the cold extrusion process. So the extrusion presses can be either horizontal or vertical. Although the horizontal is more common, extrusion presses they usually, and the extrusion process, they are usually hydraulically driven, which is especially suited to semi-continuous and direct extrusion for long sections. While the mechanical drives, like in the case of the forging as well, the mechanical drives are mostly used for the impact extrusion. Like in that case, it was mostly used for the impact forging. Here, the mechanical drives are mostly used for the impact extrusion, while the hydraulic presses, they are mostly used for the direct or the continuous extrusion for the long sections. So there are some other extrusion process, a specialized one. The first one itself is termed as the impact extrusion, and the other one is called as the hydrostatic extrusion. So the impact extrusion, it has high speed, shorter strokes than conventional one, and used to make individual parts. So impact is applied instead of pressure. So if you see here, the impact extrusion, the part length is small, and we are using punch for exerting the impact load, and it is used to make the smaller part. As we have, I have given an example of a cup shape in the beginning, and this is the impact one, as it is written, and it is also backward or indirect extrusion, right? Or it is also as discrete extrusion. So this process can be classified in all ways. It's an impact in nature, it is backward indirect extrusion in profile, and it is discrete based on the product, right? Or we have the hydrostatic one, to avoid the frictional effects, right, and to exert a uniform pressure onto the work part, we apply a hydraulic force onto the work material. That is known as the hydrostatic extrusion process. So it is performed, the hydrostatic one, it is performed as a direct extrusion to overcome the friction, because there is no direct contact between the container and the work part, as you have seen in the figure. And how do we do that? We fill the container with the fluid and exert a uniform pressure. So where do we use this hydrostatic extrusion? It is mostly used in the metals that are too brittle for the direct extrusion. That means if there is a friction between the container and the billet surface, there is a chance that they will fracture. So that's all for the extrusion process, although there are some specialized types that are still left to be discussed, and there are some defects of the extrusion process. The last thing, you should read section 19.5.5, that is defects. Extruded products. So you should read, it's only a half page section, so you should read by yourself. Should you have any questions, you may ask me. So that's all for the extrusion process. In the next week we are going to discuss the last type of the bud deformation process, that was wire and the bar drawing, and then we will jump towards chapter number 20, that is the sheet metal process. Assalamu alaikum.